curves. So the fundamental theorem of calculus, again, we're still talking about the definite integral. So if you have a function that's continuous over a closed interval from a to b, and f is the antiderivative of f on this particular closed interval, then the way that the fundamental theorem of calculus works, or the way that you can evaluate your integral, is first of all you do your integration. You use all your rules of integration. You evaluate, you integrate f of x. Then what you're going to do is you're going to plug in your upper bound into your antiderivative minus the lower bound. So you do your integration of a function, and then you simply plug in your upper bound minus your lower bound. In other words, the definite integral can be evaluated by finding any antiderivative of the integrand. So perform your integration, and then subtracting the value of this antiderivative at the lower limit of integration from its value at the upper limit of integration. You're still calculating the area under the curve. So when they ask me to find the area under the curve of y equals f of x over the stated interval, so what I'm going to do to calculate this area is simply I'm going to integrate x to the fourth dx, and then again my bounds are going to go from -1 to 1, since I want to calculate the area under the curve from -1 to 1. So first you want to do your integration. So what is the integral of x to the fourth? That's going to be x to the fifth over 5. And then what I want to do, and I always draw this line showing that my lower bound is -1 and my upper bound is a 1. And then I substitute. So I'm going to plug in a 1 for x, so that's 1 to the fifth over 5 minus -1 to the fifth over 5. Well, I know 1 to the fifth is just going to be 1, so that's going to be 1/5 minus. Now be careful. I see so many careless negative mistakes here. What's -1 to the fifth? -1, so I'm going to have a -1 to the fifth. So minus a negative becomes a positive. So 1/5 plus 1/5 is going to give me 1/5 plus 1/5 is 2/5. Very good. So any questions on how I can use the fundamental theorem of calculus to evaluate a definite integral? So next I have 1 over x. And again, I want to evaluate this from 1 to 5. Well, first of all, is 1 over x continuous in this interval 1 to 5? Yes, it is, because I know 1 over x has a domain of all real numbers except 0. So I know it's continuous from 1 to 5, correct? So that I can calculate the area under the curve by integrating 1 over x dx, and then evaluating this from my bounds from 1 to 5. So now my question is, what is the integral of 1 over x going to be? That's going to be ln of absolute value of x. And again, I'm going to evaluate this from 5 to 1. So I have the natural log of 5 minus the natural log of 1. Remind me again, what is the natural log of 1? 0. So what is my final answer then going to be? My final answer is going to be natural log of 5. Don't forget, guys, the natural log of 1 is equal to 0. So again, especially if that's a multiple choice question, they're never going to write that natural log of 1. The natural log of 1 is 0. So any questions on the natural log of 5? So like I said, these directions just simply said to find the area under the curve. So now when you take a look at example 2, evaluating the integrals using the part 1, we'll talk about part 2 of the fundamental theorem of calculus in a minute. So part 1 is just talking about how you evaluate those definite integrals by plugging in the upper bound and then minus plugging in the lower bound. So first of all, they're giving me my bounds from natural log of 2 to 3, and they want me to evaluate this definite integral of 5e to the x. So first of all, I want to integrate. What is your integral of 5e to the x? 5e to the x. And I want to evaluate this from natural log of 2 to 3. So I'll plug a 3 in for x, so that's going to be 5e to the third minus 5e raised to the natural log of 2. Can you simplify that e to the ln of 2? going to your properties of logs and exponentials, can you simplify e to the ln of 2? Yes, because those are inverse functions. Remember, e to the ln, that's that composition of a function and its inverse. So remember, when I have a composition of a function and its inverse, they're going to cancel out. So what's this going to leave me with? It's going to leave me with 5 times 2. So then I'm going to end up with 5e to the third minus 10. So any questions on part A? You guys go ahead and try B for me. Tangent of theta, and then you plug in pi over 4 for theta, and then plug in your 0 and subtract. So everybody come up with a 1 for part B. So any questions on how you evaluate those definite integrals without having to do those geometry shapes? We talked about this when we were talking about area that falls below the x-axis. We were talking about how the area below the x-axis we consider to be negative. And I said to you, I mentioned to you, we'll be talking about total area, where we're going to be looking at the absolute value. When we're talking about area, think about displacement. Remember, when we have this region that's falling below the x-axis, we consider this area to be negative. However, if they want to talk about total area, or think about as your total distance traveled, then what you're going to need to do is you're going to have to take this region that falls below the x-axis and reflect it above the x-axis. So that's where we would consider this region to be positive. So anytime they talk about total area or total distance traveled, that's where you're going to take the absolute value of the function in order to calculate the total area. All right, so basically, now think about your transformations. If you do have a region that's falling below the x-axis, how can you take a function and reflect it over the x-axis? What happens with it? You do what? You simply put a negative sign. You negate it. Because if you have a problem where you have to do this by hand, what you're going to have to be on the lookout for is you have to actually look at the graph and see if there's any part of that region that actually falls below the x-axis, and you may have to split the integral. All right, so let's take a look at an example of where we have to do this. So again, we want to find the total area. So again, when we talk about the total area or the distance traveled, that's where you have to look at the absolute value of the particular function. So any region that falls below that x-axis, you're going to actually have to reflect it. Now, if it's a calculator question, your calculator will take care of it for you. All right, so again, sketch the curve and find the total area distance traveled between the curve and the x-axis. So again, they're giving you sine of x. We want to calculate the total distance traveled from 0 to 3 pi over 2. So we're going to do this both ways, using the calculator as well as we're going to do this by hand. So first of all, let's take a look at the graph. So again, I'm going to graph sine of x from 0 to 3 pi over 2. So when I graph sine of x, here's 0, pi over 2, pi, and then 3 pi over 2. So I know sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1. Oops. So that's what the graph looks like going from 0 to 3 pi over 2. So notice I do have a region that is falling below the x-axis. So in order to calculate my total area by hand, what I'm going to have to do is I'm going to have to actually take the area that's going from 0 to pi, and again, this region's already above the x-axis. So I can go ahead and I can apply my fundamental theorem of calculus from 0 to pi for sine of x dx. Now, I have to take this region from pi to 3 pi over 2, and I've got to reflect it above the x-axis. So as for your transformations, the way you do reflections is you put a negative sign in front of the function, correct? So what I'm going to have to do is add from pi to 3 pi over 2 of negative sine x dx. Because we only want to worry about reflecting that region of the graph that's falling between pi to 3 pi over 2. So any questions on how you're going to handle finding total area or total distance traveled when you have to split the integral. So now I'm just going to integrate each individual part. So first of all, I need to integrate sine of x. What's your integral of sine of x? Negative cosine x. And I'm going to evaluate this from 0 to pi. Plus, now let's integrate negative sine x. So what's the integral of negative sine x going to be? Cosine x. And I'm going to evaluate this from pi to 3 pi over 2. Be careful of your negatives. So what I need to do, again, I can leave that negative sign factored on the outside of the parentheses. So I have cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. So negative 1 minus 1 is a negative 2. But then I have a negative sign in the front that's going to give me a positive 2. Watch those negatives. Plus. Now I have to plug in 3 pi over 2 into cosine. So I have the cosine of 3 pi over 2 minus the cosine of pi. What's the cosine of 3 pi over 2? 0. Minus cosine of pi is negative 1. So 0 minus a negative 1 is going to give me a plus 1. So what's 2 plus 1? 3. So any questions on how you're going to, again, if it's a no calculator question, you have no choice but to graph it. And then you're going to have to split your integral and do that reflection across the x-axis to take the absolute value. So any questions on that? So now let's take a look at the calculator. If you have a calculator, then all you can do to calculate the area is you can actually just simply evaluate this from 0 to 3 pi over 2 and put the sine of x inside the absolute value. So if you have your calculator, you can go ahead and just put that entire function inside the absolute value. So when you're doing integration, and again, reminder, anytime you're dealing with trig and calculus, make sure your calculators are in radian mode. So go to your y equals screen. First of all, the way you want to make sure you plug your function in under y1, so I'm going to go under y1 and type in sine of x. So when you want to evaluate your integral, just like we did derivatives, you want to go back to your home screen. So you can come up with your integral going under your alpha window. It's right underneath the derivative option, option number 4. So you can type in your lower bound of 0, your upper bound of 3 pi over 2. So now what you want to do is you want to take the absolute value of the function you have loaded under y1. So the absolute value you can find by going to your alpha window. And remember, alpha window option 1 is where you have the absolute value. And again, I want to take the absolute value of the function I've loaded under y1. So remember, y1 is located under alpha trace y1. And then type in your dx. You could have also, when you typed sine of x under y1, you could have put sine of x in absolute value under y1 as well, and then just selected y1 from this screen. So it's just a eeny, meeny, miny, mo where you want to put the absolute value. And then you can hit enter. Again, it's doing a lot of calculus, so just be patient. We talked about this doesn't have the most updated, and now we're on iPhone, 11, or I can't even keep track how many iPhones are out there. We don't have the fastest iPhone operating speed in these calculator memories, so be patient. So you can see we have 3.00000, which is 3. All right, so any questions on doing total area or total distance traveled from the calculator? Again, the big thing is just making sure you do that absolute value. So questions on that? Yes, Ben?
Where did the floating point math?
Floating, where did it come from?
Yeah.
That's a good question. I don't know.
You can't, so it's trying to store something in binary that's repeating, and then this is a result of converting it back. It's like if you try to add 0.333 plus 0.666, you get 0.999 if you don't do some special stuff, and that's what's happening.
Okay. So he's going to be my calculator expert. So I don't work for TI. Somebody making a lot more money than me is working for TI programming these calculators. So I'm sure it's something in the memory there. So, like you said, binary. I took binary. Isn't that a college course? I took binary. Yeah, I took something with binary numbers. It's all ones and zeros. Is it programming? Is it a programming
Like
class?
1/10 is repeating in binary, so you can't store it.
It was all ones and zeros. I remember that class, but that was years and years ago. That was a long time ago. Yeah, it's been a while. It's been a while. Okay. So any questions, guys? So that takes care of the fundamental theorem of calculus part 1. So let's talk about the fundamental theorem of calculus part 2. And this is just really, ladies and gentlemen, making sure you understand the relationship of your antiderivative with f of x. So again, you still have to be dealing with a continuous function on your interval. So if f has an antiderivative on that interval, so in particular, if a is any point in that interval, then the function f is defined by. So f of x is equal to the antiderivative of f of t dt. So what the big thing you need to understand is that this function in your integral is the derivative of f of x. So this f of t is the derivative for f prime of x. So that is that f prime of x is equal to f of x. Or in this particular case, it's your f prime of t, I should say. Now, it is a definite integral. So again, I was right the first time. It is your f prime of x, because you plug in your x. So really what they're saying, if I take the derivative of my antiderivative, their inverse operations are going to cancel each other out. So all I'm going to be left with is a function that's inside your integral, but then when I plug in my upper bound, I'll get the f of x. All right? So the big thing, in order for this fundamental theorem of calculus to take place, if a definite integral has a variable as your upper, so the variable, what you have to be careful of, has to be your upper limit of integration. And the constant has to be your lower limit. And again, you have a continuous integrand. Then the derivative of the integral with respect to its upper limit is equal to the integrand evaluated at the upper limit. Because remind me again, what's the derivative of a constant? 0. So that's why you want to make sure, because remember when you evaluate definite integrals, it's always minus that lower bound. So when you take the derivative of constant, that's why that lower bound's got to be the constant. So this is why this theorem applies. So let's just take a look at these two different theorems here. So first of all, what I want to do is I want to take the derivative of the antiderivative t to the third dt. And then I'm going to integrate and take the derivative of t to the third. So let's do this one first, and then I think this first one will make more sense. So first of all, let's integrate t to the third. Well, what's my integral of t to the third? That's going to be a t to the fourth over 4. And then I'm going to evaluate this from my upper bound of x, to my lower bound of 1. So if I plug in x, that's going to give me an x to the fourth over 4 minus 1/4. Using my fundamental theorem of calculus part 1. Now what I want to do is I'm going to take the derivative of x to the fourth over 4 minus 1/4. So what's the derivative of x to the fourth over 4? That's going to be 4x to the third over 4. Minus, what's the derivative of 1/4? 0. So my final answer is n x to the third. Notice the relationship between x to the third and the function that was in the integral.
That we change from a t to an x
It's just because the upper bound is an x.
So when we derive it, shouldn't it go back to a t?
Well, yes, not really.
Okay.
Because we integrated a function of t, but then we plugged in a variable in x into the n. But notice there's a relationship. Did I have to do all that work? No. I could have just plugged in that upper bound in for t, correct? And I could have come up with x to the third. So instead of doing all this work, integrating and then taking the derivative, again, as long as the upper bound is a variable, all I need to do is take x and plug it into that antiderivative, so my answer would just be x to the third. So this second way basically proves why that second part of the fundamental theorem of calculus works. So if I integrate and then take the derivative, notice you're undoing each other. Yes, Chris?
Wait, so like, what are you multiplying dx over x by?
Are we looking here?
Yes.
This is just a notation for taking the derivative. That's just derivative notation to differentiate. I took the derivative of this function inside the parentheses. Yes, Izzy? Basically, yeah. Because they are. You're taking the derivative of the antiderivative, so you're undoing the operation. So let's take a look at example 4a. If I want to take the derivative of the antiderivative, again, the lower bound has to be a constant, the upper bound is going to be an x. What is this answer simply going to be? This is going to be what? Cosine of what? X to the fourth. Now, what's the problem with b? There is a problem with b. In order to apply the fundamental theorem of calculus part 2, what does that upper bound have to be? That upper bound has to be an x. So I have to rewrite this first, switching my bounds. So I would take the negative in front of the integral, and I could rewrite this from 0 to x, natural log of t dt. So this answer is simply going to be what? The negative natural log of x. So don't make it harder than it is. You're basically undoing the antiderivative. When you take the derivative of the antiderivative, they're canceling each other out. Again, it's a definite integral where the upper bound is an x. All right, so any questions on example 4? Last example. And basically, we've done maxes, we've done increasing, we've done decreasing, we've done all. So this is kind of incorporating what we've already done with derivatives. But now notice, they're not giving you f of x. They're giving you f of x is equal to the antiderivative of 1 to x, t minus 1 over t squared minus 9. So they want to find the value of x where f attains a maximum value. Well, how do you do max and mins? What do you do? How do we find maxes? Relative maxes. It's been that long, chapter 4. You have to set what equal to 0? The derivative. So here's f of x. What is this on the inside of my parentheses? This is actually what? This is the f prime. So it's making sure you understand the relationship of what's inside your integral to a function. So then I know then that for part A, I have to take f prime of x and set it equal to 0 to find the critical numbers. So f prime of x is equal to x minus 1 over x squared minus 9. So any questions on how I recognize that x minus 1 over x squared minus 1 is the derivative of f of x? So now I need to set this equal to 0. So what are the critical numbers going to be? The critical numbers are going to be what? 1, negative 3, and 3. And how do I know that I'm going to have a maximum? What am I looking for when I do this number line test? I'm looking to see where it does what? Change from a positive to a negative. Exactly. So if I plug in negative 4, so negative 4 minus 1 gives me a negative on the top. Negative 4 squared is 16, and that's going to give me a positive on the bottom. So I know less than negative 3, that interval is negative. Between negative 3 and 1, if I plug in a 0, 0 minus 1 is a negative on the top, 0 minus 9 is a negative on the bottom, and a negative divided by a negative is a positive. If I plug in 2, 2 minus 1 is positive, 2 squared, 4 minus 9 is a negative. So I know between 1 and 3 is a negative. And when I plug in 4 minus 1, that's positive. So where is my maximum value going to be at x equals what? 1. So I know at x equals 1, it attains a maximum value. And again, since f prime of x changes from a positive to a negative. So it's using concepts we've known from the previous chapter, but the original problem is given to us in the form of an integral versus a function. So any questions on part A? Part B, find the intervals for which f is decreasing. How do you know f is decreasing? Thinking back to what we did in chapter 4, what has to happen with f prime? F prime of x has to be what? Less than 0. So I already know where f prime of x is less than 0. F prime of x is less than 0 from negative infinity to negative 3, and where else? 1 to 3. So now let's take a look at part C. Find your intervals where f is concave up. So how do I know when f is going to be concave up? What do we know from chapter 4? The second derivative has to be what? Greater than 0. So unfortunately, what am I going to have to do? I'm going to have to use what rule in order to take this derivative? I'm going to have to use my quotient rule. So remember, f double prime of x. So I am going to have to take the derivative of x minus 1 over x squared minus 9. So what's the derivative of the numerator? The derivative of the numerator is 1 times the denominator, which is x squared minus 9, minus the numerator. And then what's the derivative of the denominator? The derivative of x squared minus 9 is 2x, all over my denominator squared. Let's clean up this numerator. Remember, leave parentheses on here. Let me distribute that 2x. That's going to give me a 2x squared minus 2x. Distribute the negative sign and combine like terms. So x squared minus 2x squared is a negative x squared. I have minus a negative 2x, which is a plus 2x. And then I have a minus 9. Can I factor the numerator? No. So check to make sure that there's not irrational solutions coming from that numerator. Don't waste your time and do quadratic formula, completing the square, all that other stuff. Remember that lovely discriminant. It saves you a lot of time. So what happens, again, b squared would give me 4, minus 4 times a, which is a negative, times c, which is a negative. What happens with my discriminant? Is it greater than 0 or less than 0? Less than 0. So what does that tell me about solutions if I set the numerator equal to 0? Would they be imaginary or real? Imaginary. So I know I'm not going to have any critical numbers coming from the numerator, right? So don't waste your time doing quadratic formula to figure out, because you still have to check. They could be irrational, all right? Critical points that you have to check. So quickly do that quadratic, discriminant. Now, the only critical numbers are going to come from the denominator. So that's going to be setting the denominator equal to 0. So the only critical numbers are going to be negative 3 and 3. Remember, these are not points, but remember, f of x can change concavity around an asymptote. All right? So then no matter what number I plug in for x, the denominator is always going to be what? The denominator is always going to be positive. So again, when I plug in negative 4, well, that's going to be a negative 6. That's still going to be negative 16. That's a negative. That's a negative. So I know less than negative 3 is negative, correct? Plug in 0. 0, 0 minus 9, that's still negative. If I plug in 4, that's negative 16, which I know is greater than 8. So what happens greater than 3? It's still what? Negative. What's the question asking me for? Intervals of what? Concave up. Is there any place where f of x is concave up? No. So there's no interval where f of x is concave up. Because there's no place where f double prime is going to be greater than 0. Okay. So then part D. It wants me to find f prime of 0. How am I going to do that, do you think? Plug it in. I agree. But I got 3 places I could plug it in. Give me a... Thanks, Matt. Where am I plugging 0 into? F prime. Remember, I've already identified f prime of x as x minus 1 over x squared minus 9. So f prime of 0 is going to be equal to 0 minus 1 over 0 squared minus 9. So what is f prime of 0 going to be equal to? 1/9. So part E then is asking me for f double prime of 0. So how do I find f double prime of 0? I plug it in where? Plug it into the second derivative. So again, that's going to give me negative 0 squared plus 2 times 0 minus 9 all over 0 squared minus 9 squared. Don't make a careless mistake here. Negative 9's on the top. What value do I get on the denominator? 81. So negative 9 over 81 is going to give me a negative 1/9. So any questions, guys, about the fundamental theorem of calculus? Again, the big thing about that second part of the fundamental theorem of calculus is really recognizing what this function is within the interval in relationship to what the antiderivative is. All right, so any questions about section 5.5?